So we've invested a lot of time and effort into looking at metric topology and epsilon neighborhoods and interior points, but all of that was for a purpose, because now we finally know how to define an open set.
What do you mean now we know? I've always known. Those are just sets that don't include their endpoints.
Yeah, but wait, now, what did we do all of this for? I mean, didn't we just see that there's a whole lot more to it than just not including the endpoints? I mean, what was the purpose of all that?
Nope. Just don't include the endpoints. You get an open set.
Great. So I suppose you're going to try to tell me that a closed set is somehow...
That's right. Closed means that it does include the endpoints. Why have we got to make this so hard?
All right, fine. Well, let's say that I believe you. So if a closed set is the set that somehow includes its endpoints, then you need to tell me what endpoints are actually supposed to mean. How do we find the endpoints of a set? I mean, how do we even make sense of that?
It's a point on the end of the set. Duh.
But how do you define the end of a set? It doesn't make any sense at all.
It's where the endpoints are.
All right, well, it sounds like you might need to watch this video, right? Because if I believe you that a closed set is just a set that contains its endpoints, maybe we can actually make that definition make sense if we can figure out what endpoints are supposed to mean. So in this video, we're going to take your idea of endpoints and make it a little bit more concrete. We'll talk about what the boundary points of a set are, and then we'll use that as an idea to define what it means for a set to be closed. So how does that sound? Can you maybe, keep your head down and watch this video and figure out what this all means with us? I mean, is that something that we can do?
Fine. But can you please try to talk a little bit slower? I'm trying to take some notes here.
All right. So let's get into it. What is a closed set? And how do we use this idea of boundary points to give us an entry point into studying closed sets? Now, let's actually get started. So let's see if we can put this intuition about what an endpoint or a boundary point should be onto a firm theoretical foundation. So if I just sketch out the real line and some, weird random subset A, what should the boundary points, what do we want the boundary points of this set to look like? Well, the naive viewpoint, right, is that we want them to look like the edges of the set A. Anywhere that we can kind of reside such that A is kind of on one side of us and the outside of A is on the other side of us, right? Like standing on the edge of the world with the world behind me and oblivion in front of me, right? That's what I want a boundary point to be, topologically. And so, at least, we would kind of know that these 3 points, this point right here, this point right here looks like it's on the edge of the set A, this point right here looks like it's on the edge. There's this isolated point here in the middle that's we're going to have to make a choice about. But if there are 4 candidates for boundary points of the set that I sketched here, it should be those 4. So what topologically is going to characterize those points? Well, because we're living in metric topology land, everything that we do is framed in terms of these epsilon neighborhoods. So let's imagine that I'm standing at this point right here, which we want to be one of our boundary points, and I pick one of my epsilon neighborhoods. So I just stretch my arms out a little bit, where the length of one of my arms is epsilon. So what should that epsilon neighborhood at this point actually satisfy? What am I able to reach with my epsilon arms if I'm standing at a boundary point? Well, I should be able to reach in my epsilon neighborhood some points that reside within the set A, right? I should be able to reach A with my epsilon arm if I'm standing on the edge of the set A, quote unquote. But I should also be able to reach points that are not a part of the set A. So my arm span and the set A have to have at least one point in common. I have to at least be able to reach one point of the set A. But I also need to be able to reach points that are not a part of the set A. And anytime we're talking about reaching something that's not within a set, anytime we're speaking about something that's not in a set, in set theory, we use the complement of that set. So to reach points that are not in A, we'll just say that my epsilon neighborhood needs to have at least one point in common with a complement. So our definition of boundary point, our definition of being on the edge of a set, is going to be based on our epsilon neighborhoods reaching both points of A and also points outside of A, in other words, points in A complement. So then the last thing we need for this definition is, well, a couple things. I guess first we need to answer the question about, well, what about this isolated point? Right? Do we want this isolated point to be a boundary point of our set or not? Does it not make sense with what we're trying to do? And then the last question we'll need to answer is, well, how many epsilons should this definition work for, right? How far or how narrow do we need to be able to reach our arms? But before we go there, first of all, notice that if I want to consider these points here to be a part of my boundary, to be boundary points of A, notice that they didn't belong to A in the first place. We had open circles here depicting them. So boundary points of a set can come from outside of the set. So notice very carefully in this definition, A is a real subset, but X, a potential boundary point of A, does not need to belong to A. It just needs to belong to R. It just needs to be a real number. So this is unlike the definitions of interior and isolated points. Interior and isolated points of A had to first and foremost belong to A. And so all of our definitions for interior and isolated started from inside of the set and then kind of looked outwards. Our definition for boundary point could potentially start out of the set and kind of reach in, if it's possible. So boundary points of A do not need to belong to A. They just need to be real numbers if we're talking about subsets of the real line. So, what about this isolated point? What do we think about it? Should this isolated point here in the middle be a boundary point? Should it be an endpoint? Should it be an edge of my set? And if we just go back to that naive idea, right, let's say that this number is the number 8. Would I want 8 to be one of my endpoints of my intervals if we're trying to include endpoints? Well, the singleton set that contains the number 8 is another way to think about that, is it's the closed interval from 8 to 8. And if we sort of want to include the endpoints of all of our sets, if we want a closed set, then that probably means we want to include 8 as one of our boundary points here as well. So that's kind of the intuition that I think of in reasoning why I do actually want this isolated point to qualify as a boundary point of my set with respect to our definition. So let's finish up by quantifying epsilon. How many epsilons, how many different arms reaches do I need for this to work for in order to qualify as a boundary point? Well, let's imagine that I pick a point which for sure is not on the edge. I think even, Ralph Wiggum would agree that a point here kind of in the middle of that interval right here is probably not a boundary point. It's not supposed to be on the edge of my set. But if I could pick epsilon to be, if I could just find a single value of epsilon that reaches both into and out of the set, I could kind of extend one of my arms far enough to be able to reach beyond the endpoint of this particular subinterval of my set A. And then for that one value of epsilon, I would be able to reach outside and also inside of A. But I don't want that to happen, right? I want to make sure that no matter how long or how short my arms are, that I'm always reaching both into and out of the set. I always am able to reach a point of A and a point of A complement. So unlike our definitions for interior and for isolated points, for which we only needed a single value of epsilon to make them work, here our definition for boundary point needs to be able to reach inside the set and out of the set for all values of epsilon. No matter how short my arms are, no matter how long my arms are, if I'm a boundary point, I'm able to reach a point of A, and I'm also able to reach a point outside of A. So there's our definition for boundary point. Let's look at it from a couple of different perspectives also. These can be useful in the course of writing proofs that relate to boundary points. So what are some other ways to think of it? First of all, could a boundary point potentially be an interior point of A? So like this example over here, right? It kind of looks like I picked an interior point of A. How can I be sure that that is not going to qualify as a boundary? Well, take a look. Right? A boundary point can't be an interior point of A because if it were an interior point of A, that means that there would exist an epsilon such that my epsilon neighborhood is entirely a subset of A. And if that neighborhood is entirely a subset of A, that means it does not intersect anything outside of A. It doesn't intersect with A complement in a non-empty set. So a boundary point can't be an interior point because to share a point in common with A complement for all epsilon neighborhoods of myself means that no epsilon neighborhood that I choose, if I'm a boundary point, can be a subset of A. No matter what epsilon greater than 0 we choose, the epsilon neighborhood at X is not going to be a subset of A because it's going to include at least one point of A complement. So if I'm a boundary point of A, I cannot be an interior point of A. And because this definition here is symmetric with respect to taking the complement of A and replacing it with the complement of A, right? That if I look at the boundary of the set A, it's the same thing as the boundary of the set A complement. That's kind of cool. And so that means that not only will boundary points not be interior to A, they're not interior to the complement of A either, because if they were interior to the complement of A, they could not include, no epsilon neighborhood could include a point of the complement of A, in other words, A itself. Right? So requiring that every epsilon neighborhood include both points of A and points of A complement rules out the possibility that there exists an epsilon neighborhood which is entirely a subset of A, in other words, that the point is interior to A. And it also rules out the possibility that there exists an epsilon neighborhood of X which is entirely a subset of A complement, in other words, that X is interior to A complement. So another way to think about what the boundary of a set is, it's those points which are not interior points of A, but they're also not interior points of A complement. We can't be so far within the set A such that we can have a neighborhood of just A points around me. But I can also not be so far outside of A that I can have an epsilon neighborhood of A complement points around me. I have to be right on that verge in between. We say that the boundary of a set, and we use this partial derivative symbol del A to denote the boundary. I don't know the historical reasons for that. I have some suspicions. But the boundary of A consists of the set of all boundary points of A. So in this particular example, the boundary of this A would be these 4 points, that finite set consisting of those 4 points. 2 of those points happened to have started as elements of A. The others didn't. And that's kind of generically what happens. If you hand me a random set, chances are some of my boundary points will be included in me, some of my boundary points will not be included in me. And so it's a spectrum, right? We could have on one end of the spectrum a set which includes all of its boundary points, and we want to call that a closed set. On the other end of the spectrum, we could have a set that includes none of its boundary points, and we would want to say that that is an open set. Since we know what open means at this point, maybe we can try to prove this statement. Does our previous understanding of what open set should mean comport with our new understanding of boundary? Is it true that if A is an open set, then A contains none of its boundary points, and vice versa? If a set A contains none of its boundary points, does that make it an open set by the definition that we knew coming into this video? Well, let's try and write a proof. This is basically the same as the argument that we made over here for the equivalence of the definitions. Let's start on this side of the if and only if. Suppose that there exists a point X which belongs to the intersection of A with the boundary of A. In other words, suppose there exists a point of A which is also a boundary point of A. So we're negating this clause over here, which means now we need to prove that we can deduce the negation of this clause, right? We want to show, therefore, that A cannot be an open set if it includes even one of its boundary points, called X. So here's my diagram. Let's let X be a point of A, which is also a boundary point of A. And because we know that X is a boundary point of A by assumption, it satisfies this definition of boundary point. And this definition of boundary point is universal in epsilon. So that means that we can be supplied with an epsilon greater than 0. And any such epsilon greater than 0 that we choose is going to have the property that the epsilon neighborhood at X is going to contain points of A, and it's also going to contain points outside of A. And it's those points outside of A that I want to focus in on. Because this epsilon neighborhood is going to contain points outside of A, that means in particular the epsilon neighborhood is not a subset of A. If it were a subset of A, it would contain no points in the complement of A, and only points inside of A. And therefore X, by definition, is not an interior point of A. And yet we knew by assumption that X was an element of A. So here we have an element of A which is not an interior point of A. So by definition of open set, remember open set is a set all of whose points are interior to it. As soon as I find a single point of A which is not interior to A, we have completely lost the definition of open set. So, reading this from beginning to end, if there exists even one boundary point of A which is also a point of A itself, that means that A cannot be an open set by our previous epsilon neighborhood interior point definition of openness. And the shoe fits on the other foot also. Let's directly assume that A is an open set. and try to deduce that the intersection of A with its boundary must be empty. So to do that, let me pick an element of A. Right? If I pick an element of A and I'm trying to prove that the intersection of A with its boundary must be empty, that means I need to prove now that X cannot be a boundary point. Well, by definition of open set, if X is an element of A and A is open, that means X is interior to A. So that means there exists an epsilon, so again we're getting supplied with an epsilon, such that the epsilon neighborhood at X is entirely a subset of A. So everything that my epsilon arms can touch are elements of A. But if that happens, that means that this epsilon neighborhood does not touch anything outside of A. In other words, it doesn't touch any points of A complement. And if it doesn't touch any points of A complement, it means that the intersection of the epsilon ball with the complement of A is the empty set. And then looking back at the definition of boundary point, which requires that that intersection be non-empty, we've proven that X may not be a boundary point of A. So we started with this naive idea that maybe closed sets should be those sets which include all of their boundary points. And so far we have some really powerful evidence. In this video we've just shown, once we've defined what boundary ought to mean in topological terms using epsilon neighborhoods, now we've shown that a set is open if and only if it contains none of its boundary points. And so as we move from the open end of the spectrum over to the closed end of the spectrum, maybe it makes sense to define closed sets as the ones for which the boundary of A is entirely included inside of A. In other words, every boundary point of A is an element of A. We're going to start our next video with that assumption and use that as a working definition of what it means for a set to be closed. But then in the next video, we're also going to introduce a helpful distinction between certain kinds of points that we kind of want to think about as being boundaries and certain points which we might not want to consider as boundaries or we might want to think a little bit differently about. To bring that back to the example we started with, we're going to find a definition that is able to distinguish between three of these boundary points that are sort of really close on the edge of my set, and so I have a lot of my set kind of near me, even though I am always able to reach both inside and outside of the set. And this fourth point here in the middle, which is kind of isolated, right? There should be a qualitative difference between those. And in the next video, when we define closed set, we're also going to define our final type of point, which is called an accumulation point. And the accumulation points are going to be those where there's a bunch of the set that gets arbitrarily close to me. And points which are boundary points but not accumulation points could be ones like this isolated point, where I don't have a lot of the set near me, and yet I should still qualify as part of the boundary. So in the next video, we get a definition of closed sets and also a definition of what it means for a point to be an accumulation point of a set.